Alright, hello class. In this video we're going to continue our discussion on how we visualize surfaces. And in this case we're talking about graphs and level curves. And the book we use calls this level curves. I was taught that these are called contour curves or contours. But the level curve does sort of make sense. So how this works is we take the idea of traces and instead look at traces along different values of whichever variable we choose. Usually it's z, okay, but it doesn't necessarily have to be. It could be, you know, x or y, but usually it's z. So I'll just take a look at an example to get us started, and we'll get rolling on it. Okay, so level curves are essentially traces, but on parallel planes along a chosen variable, usually z. So for example, your level curves might be the z equals 0 trace, right, which is typically called the xy trace. Then you might do the z equals 1 trace, the z equals 2 trace, the z equals 3 trace, and so on. And doing this will give you, it's not so much a skeleton of the curve anymore, it's more like a representation of it at different heights. Okay, so let's take a look at an example, and hopefully that will kind of enlighten us to how this works. Okay, so to start with, let's look at an example we did last time. We already know what this looks like. This is a paraboloid. But just to give a further way to look at it. So we already did the z equals 0 trace, right? That came out to be 0 equals 1 minus x squared over 16 minus y squared over 4. Okay? So that's going to be our z equals 0 level curve. So when we moved it over, this gave us the ellipse x squared over 16 plus y squared over 4 equals 1. Okay, so I'm going to try and do a nice little set of graphs over here. All right, x by y. And so let's say that this one's in green. So the x goes out by 4, y goes out by 2, and we have the following ellipse. Okay, and of course I'm terrible at drawing these things, but here we go. Here's our ellipse, and this is when z is equal to 0. Okay, now let's look at z equals 1. Okay, when z is equal to 1, we'll get the equation 1 equals 1 minus x squared over 16 minus y squared over 4. And we can kind of do what we did before, move some things around, and we'll end up with this. X squared over 16 plus y squared over 4 equals 0. Well, this isn't an ellipse so much as it's just a single point, because the only values of x and y that will satisfy this equation, since these are always greater than or equal to 0, the only way that this can happen is if both x and y equal 0. Okay, so this comes out to just be the point 0, 0. Okay, so we'll do that in blue. We just get a point when z is equal to 1. Well, that should line up with what we already know about this, because this was a parabola that was opening down, and the highest point it ever got to was z equals 1. Okay, so that means if we were to try and do z equals 2, we wouldn't get anything that would make sense, right? Because if we had 2 is equal to 1 minus x squared over 16 minus y squared over 4, if we move things around, we would get x squared over 16 plus y squared over 4 equals negative 1, and this will never happen, right? Because, this will never happen because these guys will always be positive, so it can never equal a negative 1. Okay, so we don't have a contour for z equals 2 or anything above that. So instead what we can do is start looking at negative z's. So maybe we have a negative 1 in for z. So that would give us the equation negative 1 is equal to 1 minus x squared over 16 minus y squared over 4. So moving things around again, we'd get x squared over 16 plus y squared over 4 is equal to 2. Now, this is still an ellipse, it just doesn't look like it yet. Okay? When you divide by 2 on both sides, this gives us the ellipse 32, or x squared over 32 plus y squared over 8 is equal to 1. Okay, so if we use, I did blue, green, let's do purple. Our A is going to be the square root of 32, and our B is going to be the square root of 8. So I'm going to use a calculator to give me those values so I can get a decent graph. Okay, so that means x is going to have a quote-unquote radius of 5.66, and b is going to have a quote-unquote radius of 2.83. All right, so 5.66, well, here's 5, here's 6, so that'd be something like this. Okay, and then for the y, it's already hitting at 2, and now it will be at 2.8. So if this were 3, 2.8 would be fairly close. Okay, so we have something like this. Okay. So notice that we got another ellipse, just with a bit larger of a radii, right? The distances that were being traveled increase. So here z is 1, 0, negative 1, and then if we were to do negative 2, okay, I'll skip to the final thing. What we'd end up with is this. Okay, if we go through the same work, we should get this ellipse here. X squared over 48 plus y squared over 12 is equal to 1. So we should have a distance in the x direction of 6.9, almost 7, and in the b direction, or in the y direction, 3.4. Okay, and so on the graph, it would look like this ellipse here. And if we go down the next, right, and then if we do the same work again for z equals negative 3, we will actually get to a nice ellipse that sits on our normal tick marks. We'll go out to 8 in the x and 4 in the y. Okay, and we can continue this process on, And what's happening here is as x decreases, we're getting ellipses with larger and larger radii, okay, as we go on. So we can think of it now as a bowl opening upwards. Okay, imagine we're looking at it from above here. Okay, so let me show you what this looks like on a 3D graph. All right, so when we take a look at the graph, and if we put these level curves along on the z height where they belong. So here's the first one, which is that point, right at 1. Here's the one that was on the xy plane. And so if I show the xy plane, okay, we can see what's going on there. Let's get rid of that. Then here is the z equals -1 level curve. And if I put in the plane, this is the plane z equals -1, and you can see what's happening is it's basically showing what this surface looks like as it crosses through that plane. So what level curves do is they show us what's happening at more than just the xy plane. It's any plane that we decide to look at. Okay, so here's our level curves. All right, and if I get rid of, let's get rid of the axes, but show the xy plane, we kind of get a sense of what's going on here. This blue point is above it, this green curve is on it, and the others are below it. Okay. So I'll bring the axes back, and then let's take a look at the surface itself. Alright, so here is the surface itself, and as you can see, what these level curves are doing are tracing out the contour. That's just why I like to call these contour curves. It traces out the contour at each particular height. So if I bring one of these planes back in, this one in the purple is just showing the curve that is made when we intersect this surface with the plane. This one was z equals -1. Okay, and if we go down a level, here's z equals -2. And then z equals -3. Z equals 1. Notice that this plane only hits the very tip top of this. And then the xy plane. Okay, so while we may not have needed this for this particular example, because we have what it looked like from the traces pretty well. It's pretty easy to see what was happening with the traces. Let's take a look at that example that gave us problems the last time. All right, so here I want to find the level curves. And sometimes you'll be told which level curves to look at. If not, you just do what makes sense. Find 0, then plus and minus 1, plus and minus 2, plus and minus 3, etc. Until you get things that make sense. If you ever find one that has no solution, then you just know that the graph doesn't exist there. So we want to find the level curves of this. All right, now what I like to do is, remember last time where we were just continuously solving this equation over and over again with a different z value? I'm going to go ahead and do that now. So I'm going to move these guys over to get an x squared over 25 minus y squared is equal to a 1 minus and I'm going to call it a z star, because this is what I'm going to be plugging the z values into. Okay, so when we plug in, we'll start with z equals 0. So let's do that in blue. Right, z equals 0. We get this: x squared over 25 minus y squared is equal to 1, and this is that hyperbola. Okay, since it's the same hyperbola that we graphed last time, I just went ahead and did it here. So this was the hyperbola where x went out -5 to 5, y went up -1 to 1, and since the x was the positive guy, it opens along the x direction. Okay, so there's our hyperbola. Now let's see what happens if so let's see what happens when z is equal to 1. And this is going to be kind of strange, because what we're going to end up with is x squared over 25 minus y squared is equal to 1 minus 1, which is 0. So now we can move that y squared over to get x squared over 25 is equal to y squared. And now this means that y and x, well, we can either do, this tells me that x over 25 is plus or minus y, or y is equal to plus or minus x over 25. Because what ends up happening, I'm going to do it this way, this means y is equal to plus or minus, it's the square root of x squared over 25, so it's plus or minus x over 5. Well, what does that mean? Well, it means that we have two lines. We have a positive one and a negative one with slope 1/5. So this is actually fairly strange. But if we just think about it for a minute, positive 1/5 x, well, both of these have y-intercept 0. So rise over run. So as we go out 5, okay, the line goes up 1. Okay, and then we have the same thing, but the negative version of it. Okay, so this is the line y equals 1/5 x, and this is the line y equals -1/5 x. That's kind of odd, isn't it? Well, yeah, I'd say it is. But when we get to, when we start looking at the graph, I think it will start to fit in. But usually, whenever you have a level curve that intersects itself, points like this, okay, once we get to the graph, it'll be easier to talk about, but these are fairly strange points, okay, and we'll have the tools to deal with these a little better. But notice that these lines are basically the lines that this hyperbola was following. Okay, that's odd. All right, now let's take a look at x equals -1. All right, and I think I just said x. It's let's look at z equals -1. So that would be x squared over 25 minus y squared. And then here, if we go back up to our formula, it would be 1 minus -1. So 1 minus -1, that will be 2. And this is another hyperbola. Okay. So this will be another hyperbola. When we divide through by 2, we're going to get x squared over 50 minus y squared over 2. is equal to 1. So it gives us a hyperbola. Okay, where x is going from negative square root 50 to square root 50, and y is going square root 2 to negative square root 2, and the x term is still the positive one, so it should open horizontally. Okay, now I'm not comparing these exactly, but what we should notice is the square root of 50 is going to be larger than 5, which is the square root of 25. So the other one we had should be, you know, around here, right? It's going to be smaller. So it looks like we're spreading out. Okay, and if I take another step down to negative 2, we'll get x squared over 25 minus y squared is equal to 3, which will give us x squared over 75 minus y squared over 3 equals 1. So that should give us a hyperbola that's moved out a little more. Okay, I'm not doing it exact, so I'm about to go to the software. Okay, so here in the what was the color I started with there? Blue. Here in the blue, this was z equals 0. Here in the pink was z equals negative 1. Then z equals negative 2. And then we'll do one more here. Z equals negative 3. Be x squared over 25 minus y squared over 1 is equal to 4, which will give us x squared over 125 minus y squared over 4. Whoops, sorry, not 125, just 100. Okay, equals 1. So this will actually bring it out to 10 by 2. So we'll be out here at negative 10 and 10, and y will actually get up to 2 in that case. So, all right, something like that. So as the z's go down, our hyperbolas are spreading out. Okay, but when we get to z equals positive 1, we have this, which is a strange thing, right? It's this weird little X shape. So let's see what happens when we start going in the positive direction. So now let's try z equals 2, z equals 3, etc. Okay, so I'll do these over here. Let's say I do z equals 2 in yellow. So z equals 2, if we remember, our original formula here was x squared over 25 minus y squared is equal to 1 minus the z value we plugged in. So this is going to give us, and it's going to seem really strange at first, but we're going to get x squared over 25 minus y squared is equal to negative 1. Right, so the 1 minus 2 will give us negative 1. And so what happens is this is another hyperbola. Okay, but it's going to be opening upwards, because if I move this negative over, I'll get negative x squared over 25 plus y squared is equal to 1. So this is going to be a hyperbola that matches the same information as before. The x goes out from negative 5 to 5. The y still goes negative 1 to 1. However, instead of We still have the same lines here. Instead of opening along the x-axis, it opens upwards. Right? And it's going to be very, very shallow compared to the others. All right. So we get essentially when z is equal to 2, if we go back here, what happens is, notice, from z going from -3, as we get closer and closer to 1, these hyperbolas are coming closer and closer together to this x value, and then they flip. And they start going this way. So I suspect that the next hyperbola that I look at is going to do this. So let's see. So this was z equals 2. Okay, so z equals 3. I imagine that's what's going to happen. And yeah, when z is equal to 3, let me not take us completely off the writing surface, we'll get x squared over 25 minus y squared is equal to -2, which brings us back to x squared over 50 plus y squared over 2 equals 1. However, reversed. So it's the same hyperbola we got over before in pink, but flipped around. Or I shouldn't say the same, but right, this one is another hyperbola that opens upwards, but should start further out than this one did. Okay, so all this together on a 2D plane is kind of tough to glean what's going on, but if we look at it in 3 space, it should hopefully be a little nicer. All right, let's see. Okay, so here we are in 3 space, and here's that first trace that we had done before on the XY plane. Okay, and then here we are when z is equal to -1, when z is equal to -2, when z is, let's see, did I have -3? Nope, so that's just 0, -1, -2, okay. Then, when z is equal to 1, we get these 2 lines here. And then when z is equal to 2, we get this. And when z is equal to 3, we get this. Okay, so when we put all these together, and okay, so let me get rid of the axes real quick, and you can kind of see in a better way exactly how this shape is constructed. Right, so what ends up happening is as z increases from the negative up to 1, these hyperbolas get closer and closer together until they finally meet, and they meet in this line. And then they start to spread out in the other direction. Okay, so if I fill in the surface itself, okay, so here's the surface itself put in, and you can see that these level curves give a much better job of tracing out what's going on. Okay, now, what I wanted to show specifically is, remember I said that usually when these lines cross each other, something's going on there? And what's going on is, if we look at it from this direction, you see that in this direction we have, looks like a maximum, right? This curve here would be a maximum. And if we look at it in this other direction, we see the curve is making a minimum. In fact, these are our traces from the other, from the traces from the last video. All right, so if I clean this up a little bit, and these are just the XZ trace and the YZ trace on our surface. Okay, notice that here they meet, but one is a parabola that opens upwards, and the other is a parabola that opens downwards. If we then look at, oops, wrong one. I believe it's, yeah. If we now look at this level curve where they meet, we see that this has a level curve that's crossing itself. That's not a function in and of itself. And whenever you see that, you have something weird like this going on. This is actually called a saddle point because it looks kind of like, well, a saddle, right? So your legs can go here and then this goes up here, okay? So, right, that is what is happening whenever you have something like this where you've got what would seem like a contradictory, right? Where you have an opening parabola opening upwards in one direction and opening downwards in the other. All right, so now the last thing to talk about are cylinders, and this is sort of general cylinders. Okay, and this comes from whenever you have something like this. If you're talking about the surface, let's say z equals just x squared. Okay, well, if z equals x squared, that means that if we were to graph this curve here, x by z, we would have just a simple parabola. Right? This would be our z equals x squared. Now, this is going to be our level curve for any y. Right? So when y is equal to 0, this will be the level curve. When y is equal to 1, this will be the level curve. When y is equal to 2, or negative 2, or 10, or any y we can think of, okay, we get the same graph because y is not a part of this formula. So if we think of maybe the y-axis coming out this way, on each value of y, we're going to get the exact same parabola each time. Okay, so it's going to look like sort of a trough in this particular example. Okay, because all we're doing is stacking the same parabola over and over and over and over again. Right, and the reason it's called a cylinder is because if we consider the surface x squared plus y squared equals 1, there's no z here. So every z trace is going to look like the unit circle. All right, so if this is our xy plane here, this would be the circle with radius 1. And again, that doesn't really look like a circle, but okay. And this would be true for z equals 1, 2, 0, 3, 4, plus or minus pi, any value that we can think of. Okay, so what that means is that when we go to start putting these on top of each other, right, we'll have this here when z is equal to 0, and this same exact circle when z is equal to 1, when z is equal to 2, when z is equal to 3, and so on. And when we put them all together, we've created basically an infinite cylinder. Okay, so, but it doesn't have to be, you know, a circle. It can be something like this, a parabola, that is simply given another dimension. So that's essentially what it is. A cylinder is a circle that's just given a height. Well, a general cylinder is any curve that is either given a height or a length or what have you. All right, so to just show it off in 3 space here, when z is equal to 0, when z is equal to 1, when z is equal to 2, when z is equal to 3, and then the full cylinder itself. Okay, so this is basically what a generic cylinder would look like. So let's take a look at an example like this. Okay, let's say we have z is equal to sine y. Well, that we would graph on the y-z plane, and sine, well, sine does this. Right, it oscillates, but this is going to be what it looks like at every value for x. So when x is 0, when x is 1, okay, when x is 2, etc., etc. So what we've created is essentially a wave. Imagine a sheet of paper that we form into a wave. All right, and to look at this one on a graph, here's our XYZ space, and when x is equal to 0, we get this. So here it is on the YZ plane. Okay, there's our sine curve. And then when x is equal to 1, and you can see where it intersects here when x is equal to 1, x is equal to 2, x is equal to 3, and you can kind of get a sense of what's happening here. And when we fill this in, we get this. And let me see if I can hide the plane. There we go. Okay, we get basically a sheet of paper. Okay. All right, so that is what cylinders look like. So when you leave one of the variables out of the formula, you basically get something like this. Otherwise, if you want to see what some surface looks like, your best bet is to either look at the traces or look at the level curves. All right, so I think that's probably enough for this particular video. So I will catch you all on the next one. Cheers.